recording as well. So can someone say hi real quick so I can check your end of the audio?
Hi.
Perfect. Thank
Hello.
you very much. Okay. So what I wanted to do is give you a little bit of a history of where the use of mixed effects models in these designs came from, because I started learning about this at the end of my grad school career and into my postdoc. And at the time, it was somewhat of an uphill battle because in the world of cognitive psychology and cognitive aging, there was a whole lot of use of just standard linear models techniques, including repeated measures. ANOVA was the go-to analysis. And so I found myself having to explain to people like why they would want to invest in something new, what it could give them over their old techniques, and what problems it could solve. So I just wanted to give you a little bit of background on that. I may be preaching to the choir at this point because you all are here, obviously, but I think in terms of addressing potential comments from reviewers, as well as from potential collaborators who might want to know why you're doing things a certain way and how it relates to what the other options are, then this kind of thing will help you to be a little more well-rounded, so to speak. So motivation and examples is what I wanted to do. And I only have 45 slides. I don't know if this will take the whole time, but if not, I'm sure no one will be super sad if we end a few minutes early. No one's going to be really, really sad, right? I'm not going to bum you out to keep you late at work, away from your lives and your friends and your families. Okay, so like I said, when I was in graduate school, everything was about ANOVA, and that's because it was a very useful technique for a lot of designs. So we have different flavors of ANOVA, as I tend to call them, between subjects, or what I'd call between groups. You know, when you have a design in which people are assigned to separate groups and they have one outcome that you're to analyze, that is analogous to putting in a categorical predictor in a regression model in which you would have if you have C categories, you have C minus one slopes that you would need to fully differentiate all of the group means. Then we have within group, in which case there would be no between group assignments of different people, but people would do repeated things. So I might ask you to do a task, for instance, a dual task, do a task when you're not doing anything else versus do a task when you're doing something else. And then the difference is the discrepancy in performance under those conditions. And so you're holding yourself constant. It's thought to be more powerful in most cases if you can avoid problems of carryover and such. And then there's what's known as split plot, which I remember learning this term and I'm like, what the hell is that? It refers to farming somehow. It's like when you put plants in different rows, and it's a particular kind of design whose roots are in agriculture. So that's a like a stat word, but it just means a mixed design. So you have a between group manipulation at the same time you have within group manipulations and potentially more of each of those. And so some people call that a mixed design, not to be confused with a mixed effects model, which is what you're here to learn about. And each of these is expandable, so you can add on pieces to allow more complexity in estimation or questions to be answered. So for instance, you can have multiple different group assignments or measured predictors. You can have main effects of continuous covariates. So I'm making this point specifically when people talk about ANCOVA, they are adding a predictor that is a person level piece of information, and it can be continuous or categorical, but it's person level. There's really no way to have covariates at the trial level. For instance, if you have multiple trials within a condition within an analysis of variance model, and you can extend it to multiple outcomes. So you can look at response time along with accuracy, for instance, and that would be MANCOVA. The problem, of course, with that is the use of ordinary least squares estimation, because in that world, everybody has to have complete data. So it doesn't help you if some people are missing some things. So repeated measures ANOVA, as we would call it for the within group version or the split plot version, anytime there's more than one outcome per person of the same kind to be predicted. It works well under a lot of conditions. It's designed for situations in which the stimuli that people are responding to, so the trials or the items, are controlled and exchangeable, meaning you know exactly why some of them are more difficult than others because you did that on purpose. Like you have full control over that situation. They're not things that are sampled from a population where they're more randomly and continuously varying. And the question then is, well, what if we have things that don't really fall under that category, like naturalistic scenes or real words? They have lots and lots of characteristics beyond what we may have measured or manipulated. How do we introduce that variability or capture that variability in a model? Repeated measures ANOVA really wasn't designed to do that. It also works best when the repeated conditions truly are discrete. So for instance, if you have the single task condition versus the dual task condition, those are clearly separate things. If you have, like I'm used to the world of visual attention studies, where you might have a visual search task and you have to find a target and there's 3 distractors versus 9 distractors versus 24 distractors, whatever you have, then like each of these is a separate condition. But what if that's not true? So in the examples that I'll talk about, one of them is presentation time. People were supposed to look at a scene continuously for up to 6 seconds, and they were measuring eye movement data, fixation, saccades, and that kind of thing during that. Well, how do you come up with repeated measures for time, especially when data are being collected every single millisecond? And what this example I'm thinking of, what the student had decided to do was to cut it into 500 millisecond bins. So like if you had 6 seconds, then you would have 12 different conditions. And that's not ideal because there's no magic line that separates, 499 from 500 to 501 as truly different. They're not. It's a continuum of some kind. So we want to be able to incorporate predictors or item feature information that's continuous and not just discrete. And then complete data, that's the big one. So if you're doing a response time type task in which people really shouldn't get it wrong unless it's an accident, then you wouldn't have very many inaccurate response times that you would traditionally remove. If item responses are missing for no systematic reason, so if you have a design in which certain trials are administered to certain people so that you don't overload them, like a plan missingness design, that would be okay. But what if that's not the case? What if people miss items that are more difficult, or that are, because of the features that they have, make them more difficult for certain kinds of people? Then not having complete data is going to be more of a problem because the missingness is informative, as we would say. It's going to be something that you need to take into account. The model needs to understand which trials were not included because they had a missing response and what the characteristics of those trials were. So let me tell you what the story that motivated where this whole thing started. These are real people. These are people I went to grad school with. So Larry Locker is at Georgia Southern University, and he was in the cognitive psych program with me I was at the University of Kansas, and Jim Bovaert is now at the University of Nebraska-Lincoln, where I also did my undergrad, and I worked there for 8 years, and he was over in the quant psych program. And one night after work, we were hanging out in downtown Lawrence, and Larry was really bummed. We were playing pool, and he was bummed out. And I asked him, like, what's wrong, Larry? And he said, my paper got rejected. I'm like, well, that's a bummer. What happened? He's like, well, my F2 wasn't significant, so they wouldn't take it. I'm like, F2 what? Like F2 ANOVA. Like, okay, I know between groups, I know within groups, I know split plot. I know all the kinds. I've never heard of an F2. So in his world, he was a psycholinguistic student, and he was used to studying the properties of words and how they affected people's processing of the words. And usually in these designs, the participants were more of an afterthought. Like these are the introductory psych students from the university who have to participate in research for college credit. They're the ones sitting in his experimental lab going, it's a word, it's a word, it's a word, it's not a word. Exactly. You've been through these sorts of studies, or you've subjected people to these studies. I've been on both sides of that. So at the time, there was a debate in their literature about what the best way was to analyze data from these kinds of experiments, whether you should do an F1 ANOVA, an F2 ANOVA, or both. So in his world, he was usually using what is known as a lexical decision task, in which as quickly as possible you have to decide if a given stimulus is an actual word or a non-word. And so they have to construct the non-words very, very carefully so that they have the same types of properties as the words, the same pronounceability, the same, close to the same number of letters, same syllables, all of the stuff. I'm not a linguist, so if anyone here knows more about linguistics, you can please correct me if I'm saying anything wrong. And they usually collect just response time, thinking that you should know the difference between a word and a non-word because they're not trying to assess English language knowledge per se. These are not difficult words. And accuracy is usually near ceiling. So the question then is, how do you fit these data into some kind of an ANOVA? And there's 2 different ways to do it, and both of these are based on different strategies for data aggregation. And this all goes back to a famous paper that was published before I was born known as the language as fixed effects of fallacy. And when this came out, it made everybody mad. Like if you go to the journal after it, there's this long list of reply papers. It's like, nah, I'm right. You can't do it that way. And it was like a whole thing. So a brouhaha in the 1970s, if you will. So what is an F1 ANOVA? What's an F2 ANOVA? The question is, how do you aggregate? So just to make a simplistic example here, let's say that I have two different dimensions that I am manipulating words on. So I have dimension A and dimension B. And I have a fully crossed design where there's up to 4 different kinds of words from these two combinations. And I might have 100 trials that go into each of these, so different items or trials in this case. So an F1 ANOVA would aggregate to the subject level. So what we would do is take the mean over those 100 trials within one condition, save that number, do the same thing for the other 3 unique conditions, and then feed those 4 means into a within subjects ANOVA. So in the notation here, RT would stand for response time, C stands for condition, and S stands for subjects. So you can think of this as 4 lines of data for a person where we have an indicator as to which of these 4 conditions it was based on A and B, and we have an indicator for which subject it was based on their ID number. So a linear model's representation of a within subjects ANOVA would look like this. I have some kind of fixed intercept. I have the main effect of A, which would be when B is 0. I have the main effect of B, which would be when A is 0. And then I have the interaction of the two. And each of these gammas, the little Y-looking thing, that's what I'm going to use for fixed effects. These 4 fixed effects then are going to perfectly recreate those 4 means because you have 3 degrees of freedom and you have an intercept. And so this part is going to perfectly get those means right. The question then is, how do we account for variability around those means? And this model does so by saying, hey, well, all 4 means came from the same person, so why don't we control for which person it came from? And this term right here, this U term, is going to become what we'll call a random intercept for subjects. Intercept, because of the U here, it's the idea of a constant mean difference. So we would give each person their own mean across the 4, and then let U be the deviation of that mean from the grand mean of the overall sample. Then E would be whatever's left. So how come in this condition my mean is higher than what it was across all 4? How come this one's lower? That's E. We don't know what. So that would be the residual in the analysis, and it would be considered a condition by subject interaction, essentially, that it becomes the residual. You can't figure it out. So this is what Larry had done, and he had gotten a significant result. And unsurprisingly, he had a whole lot of people in his study. The F2 was a thing that was preventing him from being published, and this is an aggregation from the opposite perspective. So the F2 is what a linguist would do to get rid of the psycho part. We average over the people. So now the items are the star of the show. So this is an item level analysis. And because it is separate items in each condition, it would be considered a between groups ANOVA instead. So now I have a subscript of I to keep track of which item it is. But functionally, this is being treated as a simple random sample where the items are independent. So we've averaged over the people, the subjects, and we can put in the same information in terms of whether each item was part of where it was in A, where it was in B in their interaction. And then E is the residual that keeps track of all remaining variability. Why was this item's response time on average higher, even though I know all about its status with respect to A and B? I don't know. So that's just unexplained residual. And this one was not significant. And so Larry's paper was rejected. So when I heard about this, I was like, this seems sort of weird. Like each of these analyses is throwing away information. The F1 collapses across items within the same condition, meaning you are assuming that that variability doesn't matter, is non-existent. You're treating items as fixed, as if they're like perfectly determined in terms of A and B and how they make an item different. The other one, the F2, is throwing away all the information about the people. And as a psychologist, that made me really uncomfortable. So how can you pretend that people differences, individual differences don't matter? I heard several of you say that word, right? Individual differences. They're literally removing them from the analysis and just focusing on word differences. So we're assuming that people are completely exchangeable as well. So there are historically proposed resolutions, and this was part of the long contentious debate in the 70s. There's F prime, which I'll show you, something called min F prime, and where they had landed was this F1 by F2 criterion, where both ANOVAs had to be significant, otherwise your effect was not believable. But neither model is complete, and as we say in the States, two wrongs don't make a right. So let me show you the problem from a more mathematical perspective. And if you're like, I don't want to look at this, that's fine. I'll just tell you in words what's happening. So this is from the 1973 paper where he was showing like more specifically what the problem is. So this is a design in which we have items that are being manipulated. So they call that a treatment effect, like the effect of A or the effect of B, for instance. And then we have items that are nested within treatments. We have differences between subjects, and we have treatments by subjects, and then we have subjects by items within treatments. So that's all the potential sources variability that we would have in the original data, not the aggregated one. So if you want to build an F-test to test the effect of treatment, you would use these two lines if you were in an F1 ANOVA, where treatment by subject would be the error term, and the effect of treatment would be in the numerator. But the way that F-tests work is that it's supposed to be a ratio of what you know to what you don't, in which know means one new idea, not two. But in this design, the numerator of the F would differ from the denominator by these two sources of information, differences across treatments and also differences across items. So there's a confound there. If I go with the F2 ANOVA, I have the same problem with just a different denominator. In that case, then I would have items within treatments as the denominator, but the numerator differs by two things: the effect of treatment, which is what we want to care about, and then treatment by subjects, which is the extra thing that sneaks in there. So this doesn't work. What he did is figure out the math for how you can create the right F-test that differs only by one term in the numerator, and this is the math that you can use to get there using mean squares and whatnot. So this works just fine, except that it requires ordinary least squares estimation in 1973, and it also requires complete data. So if any subject missed any word, any item, you'd have to throw out that entire subject's data or that entire item's data. Not ideal. So in practice, this is a lovely idea. It was a very elegant solution in 1973. It isn't going to work. So folks figured out how they can hack this into something they could compute with incomplete data. So we have what's known as min F prime, which is the F1 and F2 ANOVA results recompiled. That's been shown to be somewhat conservative in the literature, so people didn't like it, so then they stuck with the F1 by F2 criterion. But as he's telling us more about this and I started looking into this literature, I thought, hey, wait, I'm learning multi-level modeling. I think I can fix this because I can throw a multi-level model at this and it's going to be wonderful. So how about we do that? So first off, what is a multi-level model or a mixed effects model? Because it goes by a whole bunch of different names depending on who you talk to. So that's why I refer to this as multi-level model word salad. So if you talk to somebody who is from biostat or StatStat, you would probably hear this called a linear mixed effects model, where nonlinear might mean generalized or it might mean something else. It just sort of depends. And the term mixed effects means that the model has fixed effects, which all models have by default. So like when you learn your first regression model, that intercept and those slopes, those are fixed effects. And what fixed means is constant. It means everybody gets the same. Like there is one intercept and it applies to everyone's score. There is one slope and it applies to everyone's score. These models differ in the addition of what is known as a random effect. A random effect is a variable, not a constant. It allows different units of sampling to get their own version of the model parameters, such as intercepts, such as slopes. And we usually think about it as random effects across people, but it could be random effects across items or other kinds of meaningful units of sampling as well. Random coefficients, I've also heard this called because effects and coefficients are synonyms. Hierarchical linear models, so several of you use that term. Is this what you meant by hierarchical or something else? That's what you meant? I see one nod. Because I know hierarchical models could mean many things. But if you say HLM, that usually means this. Other special cases. So repeated measures ANOVA technically is a mixed effects model because you have this random intercept, even though you're usually estimating it on aggregated data. Growth curve modeling. So longitudinal analyses where your focus is on individual change. And if you want to sound fancy, you can throw the word latent in front of it. And that doesn't mean anything other than the fact that you estimated it using structural equation modeling software instead of mixed effects modeling software. If you want to actually look at change in a latent variable, that's not called this. That's called a second order growth model or hierarchical factors growth model. And there is a connection to the world of SEM that I'm happy to give you resources on if you're interested in that. I've covered that in other places. Daily diary studies with in-person fluctuation studies, ecological momentary assessment stuff, that's a special case of this, where we wouldn't be focused on individual change that stays around so much as individual fluctuation. That's a little more temporary. Clustered or nested observations. So I work in the College of Education where there is no such thing as a simple random sample, like ever. The subjects are always nested in some kind of way. There's children clustered within classrooms or teachers, teachers clustered in schools. We have undergraduates clustered in dorms or majors or things like that. So there's all sorts of examples of that in real world research that's conducted in observational settings. Cross-classified models, so a couple of you mentioned this word. That refers to designs in which there's more than one source of nesting. So for instance, if I'm looking at a child's growth over time in an academic context, each year the child moves to a different teacher in a different classroom in the US setting. So in that case, I could estimate occasions nested in children, occasions nested in teachers, and children and teachers are crossed. That's one example. The context of cross-classified models that we're going to be discussing is when we have trials that are nested within subjects. Trials are also nested in items, and subjects and items are considered crossed. So there's a lot of cases where that shows up in experiments as a consequence of being wanting to cover all your bases and have things as separated as possible. These models, though, if you're estimating them using any kind of maximum likelihood, including Bayesian models in which it's maximum likelihood plus prior information, then we don't have to have complete data. You don't have to have everything fully crossed to be able to work this. And then also, I heard some of you say things about measurement models. Guess what? Measurement models are mixed effects models. If you fit a Roche model, that is the same thing as a generalized linear mixed model on a binary outcome. So there is a lot of overlap with other disciplines on the same technology because random effects are the same thing as latent variables in an SEM measurement context. So if you understand that tie, then that gives you a whole lot of space to work in to be able to customize your model for whatever you need it to be able to do. So this is a huge, huge world in terms of what types of designs it lends itself to and how customizable it is. I prefer the term multi-level model, but you'll also hear me say mixed effects model, and I think that's what I wrote in your abstract as well. Okay, so 916 for me, 416 in Germany. Anyone later than that? No, not taking over your evening, am I? No, we're good. Okay, how are we doing so far, folks? Good. Okay, I gotta give you the thumb system. So this is another throwback that I started during the Zoom era, but I use it in person as well. So thumbs up means you're okay. Thumbs down obviously means I'm not okay. And then there's thumbs sideways, like so-so. I'm hanging in there. Okay, so how are we doing on the thumb scale? Everyone's up so far. 2 thumbs up. Oh, and it blows up when you do that. I just learned this the other day. We got fireworks. We just graduated a student yesterday on Zoom, and so we all did this to have fireworks. When we called them back in and said, "Congratulations, you're a doctor," which is the best moment for everyone involved. But, so yeah, do you have questions about any of this, or is this ringing bells that you want to share? or ask about. Because ultimately my goal is to help each of you as best I can. So hearing, personal questions and linkages would be helpful. No, we're good so far? Everyone's shy? There's a hand. Anna, go for it.
I think I'm always a bit confused with when things are crossed, and also example went so fast. Could you just repeat that with the children and they grow up and then they were with different teachers? Like,
Yes.
and also, does it somehow, how can I even ask what I want to know? Does it affect, like, is there a problem if we miss that something is crossed and we analyze it as if it is not crossed? Like, does it lead to a different type of variant or whatever? Yeah, I think you
Yes.
know more or less.
Yeah, I think I know where you're going. It's because I have future slides in my head as I'm rattling through this that you haven't seen yet, and so I'm pulling from a point of reference that you don't yet have. So yes, happy to clarify. So an easy way to figure this out is if you have a design and you can reasonably make an argument that it's nested this way and it's also nested the opposite way, then the answer is it's not nested and it's crossed. So the example that I have with Larry's data is exactly that kind. So I will save elaboration for that one. But the other example I gave you, so like my son is in the 3rd grade, and next year he'll move to the 4th grade and he'll have a completely different teacher. But nonetheless, the school might be interested in measuring his progress, but he is not his own entity. His teachers obviously have a strong effect on him, and the cohort that he's part of has a strong effect on him. And in our system, we can't really separate those because they're tied together. So if he's in a classroom with a truly excellent teacher, or if he's in a classroom full of really smart kids who are on task and they're not distracting him, like his education hopefully would be better, but we can't tell what the effect of that is. So in that situation, if we had access to long-term longitudinal data for the children as they move across the grades, and also for the teachers, right? If you think about them as the unit of analysis, this is our 3rd grade class this year. It's not the same class that I had last year or that I'll have next year, but I'm still a 3rd grade teacher. So in that type of model, we would say that occasions are nested within students, for sure, but occasions are also nested within teachers. And students and teachers would be considered crossed dimensions because each student sees more than one teacher and each teacher sees more than one cohort of students. Trying to think of, so yeah, and just to add to this, in the States, there is a move to try to hold teachers accountable using these kinds of models where they would essentially control for teacher differences as fixed effects or random effects, and then they would use those sources of variance and your relative standing relative to the rest of the teachers as ways to increase your pay or eliminate it. So it becomes like it's a punitive kind of thing in that case, which is really problematic if you think about the consequences of you being wrong in getting these models right. So I see another hand, but just to wrap up the end of that question, the consequences depend on how you've screwed it up. So if you have variability due to some source of sampling, like items, and you pretend it's not there, then any fixed slope that has to do with item differences is probably going to be incorrect in terms of your inference about it. Like the estimate itself might be okay, but the standard error would probably be too small because the model doesn't understand that there's other sources of variability for differences across items than just what you think it should be. The items aren't really exchangeable in that case. And the same thing would be true about people. Does that help for now? And more later, potentially. More later, I promise. Tian, did you have a question?
Oh, yes, I have a, I don't know, a rather basic question.
I love
I
basic
always
questions.
find,
That means I can answer them.
I always find a bit hard to understand is does multi-level models have to be between subject design, or can it also be like within subject? Like, for example, as a school case, can I say like for language, I measured reading, listening, and speaking. So I have like different measurements, but it's also different level. One level is subject, another level is within the measurement. I don't know how to describe that. So it's also nested, hierarchical.
Yeah, you can have combinations of between and within, and things can be manipulated or they can be observed. Like basically whatever data you have, it just depends on what the structure of the sampling is. So if you have, did I hear you say you have conditions or you have outcomes within persons?
Yes, so I'm thinking about for each people, maybe they receive the same manipulation, but the manipulation are nested. So in a sense, this is more like how to say that, latent parameters? No, not latent. Hmm.
I'm not sure
Yes,
what
this is the
word.
part I'm get confused.
That's okay. That's okay. I'm not sure what word you're looking for, but I think I follow. So if everybody does, like, goes through the same manipulation,
Yes.
okay, then yes. What I would say is that in that case, you can think of each person's unique outcome to a unique condition as like what you're analyzing, and outcomes are nested in people because each person has, four of them or whatever. But then outcomes are also nested in conditions. So at the start of it, they would be crossed. However, like in Larry's example, once I put in fixed slopes that keep track of which condition is which, so if you had four conditions, you need three slopes. That could be, two main effects in an interaction. That could be one categorical variable with three levels to it. Either way, it's just three slopes and an intercept, and you've got your four back. Then once you put in fixed effects for which condition is which, they're no longer crossed. Like you've saturated that dimension because you've said why there are condition differences. It's because of these three slopes. So you've controlled for that level of sampling. Then that goes away, and what you have left is just what you can think of as condition by person interaction is your level one. It's your individual responses nested in people that are your level two, because the other level two is gone once you control for it with A, B, and A by B.
Mhm.
And the same thing happens in time, by the way. So the example of students moving classrooms over time, once I control for what year it is, right? Like, is it the fall? Is it the spring? Is it occasion 1, 2, 3, 4, 5? Like, once I put that in the model, then there should be no more occasion mean differences as a random factor because you've fully controlled for which is which. So that goes away, and then occasions by persons by teachers was left at level one. And we usually just say occasions as shorthand, but that's really what it means because all the other pieces have been separated or controlled for.
Okay, thank you.
Sure. Others. There we go. Nicola? Nicola.
Yes. Can you help me where to place, let's say, cognitive models in this list? So FPT models or sequential sampling models where we have latent cognitive parameters that produce behavior. So there are also hierarchical versions or multi-level versions of these kind of models. Would they fit in here, or is that a conceptually different category?
I don't know those models well enough to tell you off the top of my head, but if you could point me towards an example, like if I can see an equation in a little bit of text, then I could probably tell you. I can tell you this much though, when people say latent, they mean some kind of random effect, probably. So if it's some kind of like processing characteristic that you think varies across people, that's a latent variable random effect of some kind. And so in this framework, random effects are either intercepts for some kind of constant mean difference or an asymptote potentially, or a slope, meaning a reaction to something. The rest of it is, are you predicting continuous outcomes directly, or are you using link functions to predict something that's not continuous? Do you know that much?
Okay, from the top of my head. I'm thinking, I don't think I can answer or reply from the top of my head.
Fair.
Um,
But if you can
yeah, I
either,
have to
if you can email me something, I can take a look at later, or I'll share something with the group if you find it. I'd be happy to try to guess. But
Okay.
my guess is that there's also some nonlinearity at work in those kinds of models because you wouldn't expect, linear things to work in continued processing like that. But I'd have to look. It's been a very long time since I had my cognitive psychology hat on, and I'm not sure it fits properly anymore.
Okay, I'll bring something next time.
Yes, or you can do it in the meantime since we have a week in between, so I can try to take a look at that. Other questions or examples from the worlds in which you live? I never owned a personality psychology hat, but I had some friends that wore them, so I can try that too. Okay, then let me give you the end of the story here. So I was learning about multi-level modeling in the context of my research assistantship in graduate school, in which my supervisor needed me to learn growth curve modeling specifically. So I was working on the longitudinal side, trying to figure this stuff out. We did not have any classes on it, by the way. I had a book. I had the Snyders and Bosker's multi-level analysis book, and I don't know if you know this book, but it took me like a day, a page, give or take, to get through it because I kept having to go back, and I wasn't used to seeing anything that's on the technical side like that was relative to what I was used to at the time. But in learning about occasions nested in persons, which it is true once you remove the crossing by controlling for occasion mean differences, I thought, well, this design of Larry's where he has items in persons, like item responses are nested in people. So I can solve this. I'm going to do a multi-level model and it's somehow going to fix it, right? Whatever problem there was with the F2 ANOVA, I'm just going to fix it. So this is how I envisioned it. We have the original data per subject. What if we don't collapse? What if we don't aggregate all of the items that are the same kind up to a condition mean and use those means as data? What if we just leave the data in their original form? So each row of the data set would be a specific response to a specific item from a specific subject. And we can analyze all of that at the same time. So my version of the model is I was thinking of, well, level one is each individual item response from each individual subject is a function of these betas, which are taking the place of fixed effects because they become placeholders. So this is a traditional hierarchical notation. You will often not see this in cross designs because it gets ugly very quickly. But the idea is that, oops, this should not be a P, by the way, make that an S. I will fix my typos afterwards. This is because I continuously go back and forth between whether I have persons or subjects, and I had persons in some of this and tried to turn it all into subjects and I missed a P, so I apologize. But we have the effect of A, the effect of B, the effect of their interaction, and each of those then is given the fixed effects that we saw before in the F1 analysis. Here's the random intercept of subjects. So this is how I was thinking about it, and the benefits of using all the original data and this modeling approach in my mind is that then you can have missing responses. They can be missing at random, which doesn't mean what it sounds like, by the way. It means conditionally missing, conditionally random. So there is a reason it was missing, but you know enough about that reason that you can still recover what the answers would have been had the data been complete. Like you have variables or other responses that are informative about the missingness. And you can also have continuous predictors. So the requirement that A and B be discrete conditions is entirely because people are trying to aggregate up to some kind of condition mean to shove into an ANOVA. But if you don't have to do the aggregation, then you don't have to have discrete conditions. You can have continuously varying item features and you can control for those as predictors. The only problem with the approach that I proposed is that it's wrong. Just a small wrinkle. It's essentially F1 ANOVA, just not aggregating the data. Like in terms of the structure of the model, it's the same thing because we are only controlling for differences between people in their mean response time. We are not controlling for any differences across items of the same condition. So this model says that there is no difference, there's no variability whatsoever among the 100 items within each of these cells. And that is really unlikely to be the case no matter how good of an experimental design person you are, especially if you're working with real stimuli like words and pictures. So this was the problem. I was thinking about this from a longitudinal perspective of between versus within. I heard a couple people say that as well. where I was thinking of I have within subject variation and between subject variation, but I don't really just have within subjects. What level 1 actually is two different things. I have why are some items more difficult than others, no matter who's responding, right? There are some items that take longer or are responded to less accurately. That's between item variation. And then I have individual trial variation that's left over. And you can think of this as a subject by item interaction term. It's not separable from the residual if you only have one combination per subject and item. So if each subject sees each item only once, then there's no way to pull apart any interaction term variability from just the residual in that case. But what we should have are these three circles right here. So if we start from the beginning of how we would think about what kinds of variability do I even have, we would start with what I call an empty model. Is this a term you're familiar with? Have you? So empty means no predictors. And I teach empty models from the very, very beginning, like when I teach regression as our first class, I start with an empty model because conceptually, that is all of the variability that there is. So in this equation, I still have response time, but now the subscript keeps track of which trial, which item, and which subject. So I'm thinking of those as three different kinds of variability. I have a fixed intercept, which would be the mean response time across the entire data set, all subjects, all items, and then E is everything that's left. So if you think about the original formula for variance, it's y minus the mean of y, summed, like squared, then summed, and then divide by n if it's maximum likelihood, or n minus 1. Like that, the variance of the e's right here would be just the variance of my outcome. Other than the n versus n minus 1 thing, they would be the same. So conceptually, like E is everything. E is all the reasons why response time differs across people, items, and their combination. So we can start taking all of that E variance, I think of it as like a sphere, like a pile in my head, and we can start to pull it apart. So why this is a problem is that this model would assume that all of the individual response times are independent, that there's no correlation between the responses from the same person or the responses to the same item. And that's unlikely to be the case because some items are going to be harder than others. Some people are just better at this task than others. So we can add a random subject intercept, which is our friend U that we saw earlier, but now with a couple extra subscripts to denote trials, items versus subjects. So this model then says, no. There should be a correlation between response times from the same person, and the reason for that correlation is right here. So U is a random intercept. It is a variable. Each individual subject would get a different value in theory, but what the model actually estimates is the variance across the U0s across subjects. So U0 is really more of an idea than a specific quantity. Like you won't get that on your output. You would have to predict it after the fact and it would not have the same information to it. So we would care about the variability across subjects in this random intercept U term, and we would care about how much relative variability is left in the residual. So this is analogous to the F1 ANOVA in terms of allowing subjects to differ from each other, but then not allowing anything about the items. So then the last step would be to consider adding the item random intercept. And so this then allows differences across items. It also simultaneously allows a correlation of item response of trials that came from the same item. So F1 ANOVA would only have the red U across subjects. F2 ANOVA would only have the blue U across items. And the proper analysis that puts everything together would be considered this crossing of the two. So if you think about what goes into an individual trial-specific response here, it's some kind of overall intercept. So what is the mean? And then you get a bump based on who you are. So people who are slower than others, their U would be positive. People who are faster than others, their red U would be negative. Then we get a bump based on which item it is. Items that are more difficult would have positive blue U values here because it would take longer to solve those items. Items that are easier would have lower values. And then E is whatever's left. Like I've already controlled for which subject this is, which item this is. I don't know why the response still isn't perfect. Everything else just goes into E. And so this would be trial-specific remaining variability. So the overall model, if I were to do it properly for Larry's data, would look like this. So we can incorporate my A and B item predictors. They would explain the U0 item variance. What's not incorporated, but what could be incorporated, is subject predictors. So why is it that some people are faster at this task than others? I don't know, but I could collect subject information about individual differences and put that in the model. And subject information would explain this U subject intercept variance. Then trial level information could also be included. So what happens when you make people sit in the room and do this? Do you think they stay diligent the whole time in responding to whether it's a word or a non-word? Are they all perfectly reliable subjects the whole way through? Maybe not. So I think there's two competing things that can happen. If it's a challenging task, hopefully they get better at it as they go along. So responses might improve as a positive slope of which trial you're on. If they lose their will to live and don't want to sit in your task anymore, then performance may decline as a function of which trial it is. But that's one thing that you could put in as a predictor, is just what is the change in performance across exposure to the task? Do people get better? Do they get worse? Is it a linear function? Is it some kind of nonlinear function? Is it both? You can have whatever specific things about that trial. What was the temperature in the room? What was, et cetera, et cetera. So the idea is that these models then have a separate variance component, a separate random effect for each systematic source of sampling, subjects and items, and then they have the residual for whatever's left that's trial specific. Okay, how's that sitting with you?
I have a question.
Please.
In the last slide, when you make like the variance decomposition, when you have like those random intercept integrate. Yeah, the last formula. For example, could you also have like, I mean, that would be like an overly complex model, and I don't know for whatever reason you would like to do that, but only in theory, for example, could you also have like an interaction between those two random intercepts or random effects? For example, if you have like the same subject item combination over multiple trials, for example, and then you have like also like a third random intercept term, which would be like an interaction between subjects and items.
Yes, if you make people respond to each item more than once, then yes, you could have a third person by item interaction variance, because you could pull apart, like, why does this person do extra good on this item? You'd have to have multiple trials to be able to observe that, but yes, you could. And that idea, you might see that under the heading of generalizability theory. So that is an extension of classical test theory that was focused on partitioning sources of variance in item, person, occasion, rater, etc. types of settings. And yeah, if you have the design by which you observe more than one unique combination, you can have a random interaction term. I've never tried to do that. It is theoretically possible. And in experimental designs in which there is more than one repetition of things, then you do start to see these sorts of extra sources of nesting or crossing as a result of that. My design is relatively simplistic, just as a starting point. I should say Larry's design. I came in on the back end. I was going to save his paper. Okay, other questions or comments? Well, the end of that story is that I didn't save his paper. It was rejected and it remained as such. But what we were able to do is take another failed experiment and publish it as the example for a methodological tutorial. I have done this a couple different times and I highly recommend it. So if any of you have data you're sitting on that didn't work, see if you can turn it into a methods tutorial and get it out of it. So I was eventually able to publish my master's thesis that way, and Larry was able to use a different data set to get a new paper. So there's a happy ending to that story. And he eventually got a job and got promoted and tenured and all the things. So he lived happily ever after from that perspective. But in this example, he picked a data set in which the sampling dimensions were relatively more balanced, so 38 subjects to 39 words. In the paper that was rejected, he had very few words, but a whole lot of subjects. So he had a ton of power for his F1, he had very little power for his F2, and that was the logical result of F2 not being significant, is the design was set up to shoot himself in the foot, so to speak. So if you care about individual differences in people, you want as many people as possible. If you care about what makes some items more difficult than others or responded to differently, you need as many items as possible. And if you care about both, you need as much data as possible. So in his condition, we have a lexical decision task. The outcome is response time to say if it's a word or a not word. And he has two word-specific predictors, low versus high phonological neighborhood frequency, which I think is something like the number of words that sound like it. Can I get a confirm or deny from any of you? No one knows? Okay, we're going to go with that then. Today I'm a psycholinguist. Put that hat on. Number of words that sound like it, I think, and the other one was small versus large semantic neighborhood size, which is number of words related to it semantically, conceptually. Let's go with that. I'm just going to say A and B, all right, because that's too many words for let's say 9:44 in the morning. We're getting there. So the first thing that we did in this paper, designed to show people how to use these models and argue to some extent why they should, was do this partitioning of variance. How much variance do we have of each kind is a logical prerequisite for what the models can actually do. You have to have variance in order to account for it with predictors. So in the initial step with no predictors, like the slide I just showed you, layering it one by one, it turned out that 24% of the variability in the overall data set in response time was due to subject differences. So some people were just faster to do this task than others. Item differences, some items were responded to on average faster than others, was 11%. And then the rest of it was the subject by item interaction residual that we can't pull apart. So just looking at this pie chart, if you think about this from an R-square perspective, variance explained, the model that we're going to fit only has these two item characteristics in it. He didn't actually have any person characteristics collected in the entire data set. A bummer for our example, but not a deal breaker for the model. So if you put your R-square hat on, what do you think the maximum possible R-square would be in accounting for response time variance using these item predictors? What's the best case scenario in terms of explaining response time variability using these item predictors? Any guesses? You can use the chat or you can use your voices. This is actually a finger question. You can make gestures on this one. It's not a math question. It's a logic question. What's the maximum R-squared you think you could get out of this model, given that we're putting two item predictors in it? We got one vote for 11%. Anyone else want to vote? 11 question mark? That's more like 11? I'll say it out loud for you. Yeah, it's 11. Finger question, just two ones right here. Yeah, these are item characteristics. Item characteristics can't explain why some people are faster than others. Item characteristics explain why some items are faster than others. And they can't explain the unique combination of subject by item either. So this is what happened in the study. There was an interaction between these things. I don't know why, and I don't remember. To be honest, it's not germane. But we had 0% of the residual variance explained, as expected. 0% of the subject random intercept variance explained as expected, and they got 30% of the 11%. So this is where effect size in these models gets real tricky real fast. The idea of how much of each part did I get, how much of each kind of variance did I get, that's what's known as pseudo R-square. That is not a term I made up to be funny, by the way. That's legit what it's called, pseudo R-square, because these things move around in a squishy kind of way. Just like in logistic regression, there's 37 ways to make an R-square, and no one's really set on which one is right because there isn't a defined right answer. But what this means is that A and B, phonological and semantic neighborhood information, they explained 30% of the reasons why the items differed from each other. That means that overall, 30% times 30% times 11% gives us 3.3% overall. So 30% of the variance sounds great until you remember that it's 30% of the 11%. And then it's not quite so impressive, but that's reality. And you can actually test whether or not the explained variance is different than 100 by asking the question, hey, do I still need this blue U item random intercept in the model? You can answer that via what's known as a likelihood ratio test, or difference in -2 log likelihood. And if it makes the model fit worse, you still need it, which was the case here. So when we looked at these results with Larry, I was like, 30%, dude, like that's not great considering you're supposed to have controlled all this stuff. And he's like, we did, we controlled this and this and this and this and this. I'm like, why aren't those variables in the model? That's the other part of it, is that when you lose this sort of, I need to have condition mean kind of mentality, there's room to put other stuff. So the same concepts that you would have learned about in your initial experimental design class apply here. You want to be able to control for as many extraneous predictors as possible, even if they weren't your focus. They're what makes the items different. That increases your power to detect the effect of the manipulations that you do care about. So yeah, all of those control variables that went into carefully building these word lists should be considered covariates in here to further improve the power to detect the item manipulation differences of A and B in his case. So this was the token example from his paper. One of the things that we also looked at is how would the results have changed if we had done the traditional F1 by F2 analysis. So we fit those as well. So we have on the bottom here the F tests for the main effects and the interaction from the crossed random effects model that we landed on. And then I have highlighted here the F2 ANOVA. And you know what? These look shockingly similar. They're kind of the same thing. The difference is that the F2 ANOVA aggregated over subjects, so they were not part of the story, and treated items as random. The crossed multi-level model did not aggregate over subjects, but there were no subject predictors. So these inferences pertain to the effects of the items. Items are being represented as random in both of the yellow lines here, and that's why we have the similarity. If we look at what would have happened for F1, then the effects are wildly optimistic. They look way too good. And the reason for that is because the 70% of the item variability that was left over after putting in the things he cared about, that's gone. Just gone, because the data were aggregated over it. So this pretends that there's no remaining reasons why the items differ from each other, let alone 70% of the variance. And so when you look at it that way, things are wildly optimistic. F prime min, which was the combination of F1 and F2 algebra thing, this is looking a little bit unoptimistic, and that's what simulations have shown too, that this tends to be overly conservative. So we end up at I think the same place. The problem with real data, though, is that you never know what the right answer is. So I will tell you this, when you look at papers and you see papers that with the same data set do an analysis a couple different ways and then try to use that as evidence as to which approach is best, you should be suspicious, because that is sus, as my son would say. He plays Among Us. You guys familiar with this game? Few people are. Yeah, I don't really understand it. They play it on the playground, apparently. They've made up an analog version in the 3rd grade to keep them occupied at recess. But it's a game called Among Us where you're supposed to figure out who the imposter is, and they use the word sus a lot. So it's sus if people take a real data set, fit different models to it, and then try to use that as evidence as to one methodology is preferable over another because you don't know what the right answer is. The answer to trying to make that better evidence is to do a simulation. So one of the things I'm going to send you, but deliberately did not do so, is chapter 12 of my textbook. I wrote a book in 2015 that I wanted to share a chapter out of, and Anna has a question. Go for it.
Yeah, actually it's on the slide before with the variance proportions.
This one?
Yes, this one.
Okay.
It says, note, this is a percentage of total variance and not the ICC.
Mm-hmm.
I was wondering if we sometimes look at these trials, because I mean, I'm trying to put it on a diary logic where we don't think about trials, but is it, because usually we just look at the ICC to say, okay, so how much of the variance is due to yes, me being a person with several answering to it on several time points, and how much is actually fluctuations because it differs on days. So is there also, when we just look at this, we just ignore this other part of potential variance, or am I lacking still a full understanding and it doesn't even exist in certain designs?
You are not lacking understanding. If I'm following your question, it's being ignored. So you're administering questions, a diary, so to speak, over several occasions, like 2 weeks or something like
Yes,
that.
for 2 weeks, every day, in the morning, midday, and after.
Okay.
And we don't, sometimes we control for the day of the measurement day, just to make sure that we don't have any processes that are happening because people are repeatedly answering to it, but we're not really looking at it from a perspective of people will answer to those things differently over time.
Yes. So if your model does not have variability attributable to time in it, you are ignoring that. The question is whether is that okay. So in that context, there could be variability because it's the first time they did it, the second time they did it, the third time they did it. There could be variability because it's Sunday versus Monday versus Tuesday. Like those are both plausible sources. Like there could be reactivity to the process. Like people usually answer differently the first time than after that. Could be reactivity to circadian rhythms or schedules or things like that. But in that type of model, each individual response is nested in persons. That's the part you do have. Each response is nested in occasion, where occasion could be which observation or which day. And if it's multiple per day, then there's 2 layers, right? That's within days, across days. And then you could estimate a random intercept for day, for occasion, and see to what extent there is variability. And that would become a cross dimension. If you try to estimate that random intercept variance and it's not really there, then no, that it doesn't matter which day it is or which time it is, and you can safely ignore that. But it all depends on your situation and your data set. It's an empirical question as to whether it's ignorable. Typically, people do ignore it, assuming as much. Does that help? Okay, thumbs up. Yeah, other questions? Yeah, you'll hear the phrase, it's an empirical question, come out of my mouth quite frequently. That just means that there's usually some kind of hypothesis test you can do to establish what evidence for whether or not you need something. Or credible interval, I don't care. I tend to live in frequentist land, but it's the same principles hold in Bayesian land. So I made up data, and this is in chapter 12. So I have a textbook called Longitudinal Analysis. It was published in 2015. I'm ostensibly doing a revision of it, but I haven't really started yet. I'm only like 5 years late, so, sorry, tell my publisher, I've been busy. But chapter 12 in this book, I will send you a copy of in case your libraries don't have it. That's really the only reading that I would recommend to start with. As we get further in, I can send some more. But in this, I made up data in which I know what the right answer is. So I manipulated the size of the variability in items and the size of the variability across subjects to a continuous outcome. And then I fit a series of models in which I had random effects for both subjects and items, subjects only or items only. Then we had no random effects at all, so sort of like the worst case scenario. And then I did the two kinds of ANOVAs to show what happens as a function of detecting predictors related to items or detecting predictors related to subjects. And what you're looking at as the values in the table are type 1 error rates. So if you fit the right model that generated the data, you get the right answers back. A little bit of wiggle in those, but nothing that I'm going to be super concerned about. If you fit a model that ignores differences between items, so the F1 ANOVA on collapsed data or the uncollapsed data with only a random intercept for subjects. So you're saying people differ from each other, but items don't beyond whatever's in the model. Then these type 1 error rates show inflation in terms of detecting the item effect, but the people effects are still fine because people have random variance left over, whereas items don't. And the same is true regardless of whether you aggregate the data up to condition means or not. If I do random items and pretend the people are exchangeable, then I get the opposite pattern. So all of the subject type 1 error rates are inflated. That is the case whether you don't aggregate the data or whether you do in the F2 ANOVA. And only when you get both at the same time are type 1 error rates protected across the board. So the take-home message is you would want to test whether you have variability across a sampling dimension, and if you do, then potentially that's explained by predictors that you care about, but that leftover variability needs to stay in the analysis. You can't pretend that you've explained all the differences across subjects if you haven't, or that you've explained all the differences across items if you haven't. That causes problems in terms of your conclusions. So this F1 by F2 thing was, I think, a well-intended strategy, but it doesn't work. Each of these is broken. Trying to put all of the data into a multi-level model still doesn't work unless you fit both dimensions as random and any other dimensions as random that you would need to. And these models also provide additional analytic flexibility to deal with things that don't fit so neatly into a repeated measures ANOVA, as well as things that don't fit so neatly into thinking of subjects as all the way exchangeable. So I've got another example I can show you a little bit about, and then two more just as just very brief descriptions of other projects. So how does that sound? Are you hanging in there? Excellent. And if anyone needs to step away to take a break or whatever, no judgment. If anyone needs to leave early, no judgment. So let me show you data from my master's thesis, which was a piece of crap that was rejected 3 times when I tried to publish it in the intention literature, and I finally got it published as the example in a methods paper. So yay me, perseverance. This was from when I lived in the world of cognitive psychology, and the study was using what's known as a change detection task. So this is an experiment in which we have a real-world scene that is shown for 200 milliseconds, followed by a gray screen for 80 milliseconds, and then a manipulated version of the image shows up for the same amount of time, followed by a gray screen. So it just looks like a flickering thing. And what the flickering does in the middle is that it swamps the local orienting cues that would have originally directed your attention to the changed location. And it makes it so that to figure out how the pictures are different, it's a very slow and effortful search. So it's thought to index visual searchability. So we had these real world pictures that were manipulated in Photoshop. I'll show you an example on the next slide, where they had up to 60 seconds to watch this and figure out the change. And if they didn't get it by then, it was marked as incorrect and the next trial started. So we ended up using 51 out of 80 possible scenes that had greater than 90% accuracy to be able to eliminate that as a problem. We had two groups of people, And this is very common, at least in the era in which I was wearing my cognitive psychology hat. We had a younger group that was filled with undergraduates from our psychology pool, and then a sample of older adults, which was mainly retired faculty and their spouses. The within-person variables were how meaningful the change to the image was to driving. So was it something that you would normally be looking at, or was it something more peripheral and unimportant? And then how salient the change was. And so this was measured in terms of like numbers of pixels changed. It was a more computational approach. And the way that my advisor had pitched this to me when he helped design the study was as a 2 by 2 by 2 mixed effects ANOVA, where I had a between subjects manipulation and 2 within subjects manipulations predicting response time. Okay, well, first problem is differences between scenes. So this is an example of the two pictures shown side by side that would be repeated in the flicker paradigm. And this is an interstate that is in Kansas City, Missouri. So it's a larger Midwestern metropolitan area. Can you see what makes the two pictures different? A couple of you see it? It's this sign that says exit only. So this would be a highly relevant change, because if you're in this lane and you don't want to exit, you need to move over post haste. That's what this means. This is one of the few interstates, by the way, where they have exits on the left side. That's very unusual. Usually it's always on the right-hand side, so drivers might not be watching for this. So we had pictures that look like this, and there's a lot of ways in which these kinds of pictures can differ from each other, besides just the relevance of the change to driving, and besides just how much of the scene that the change took up in terms of salience. So if we treat these items as fixed effects, meaning that we're not allowing leftover variability, there's a lot of reasons why some of these changes might take longer to detect than others, and effect sizes are going to be inflated if we don't take that variability into account. Missing response times was the other problem. So we tried to limit this just to the types of items that were reasonably correct, but there's still going to be differences. So in this case, the reason that people had missing response times is because they never found the change. Rarely did people give an inaccurate result. So it's not missing at random, right? It's a consequence of low performance. They weren't able to answer the question. So this is going to cause loss of power if we listwise delete this, but if we aggregate over the items that were ostensibly of the same kind, then we have a different problem. So if this is the original distribution of items within a condition, let's say that these are the item responses from someone with high ability, and these are the responses to the same items from someone with lower ability. It takes them a little bit longer across the board. Well, what if the low ability person didn't get some of these correct? What if the times that would have been the highest, the largest response times, are gone because they never found it? Well, now if I take the arithmetic mean of what's left, there's going to be bias. This person's mean might actually be lower than the person with higher ability because of this missing data. So anytime that you aggregate over information and put that aggregated summary into an analysis, it's assuming it's missing completely at random, that there's no reason that the average does not understand what it's missing. That's not going to work. The other thing is about the conditions that I had were completely artificial. So relevance and salience were rated. So I believe relevance was rated and salience was, in this study, I think it was rated actually. I had a computational version in a subsequent study, I'm confusing. And they were actually correlated. And what my advisor had done and encouraged me to do is cut them up. So this created an uneven number of trials across the conditions, and is not ideal because we're assuming these things are discrete when they're not. So to make this a little more concrete, here's a scatter plot of the items that I analyzed, and I have the relevance of the change to driving on the x-axis as rated, and the relevance of the salience of the target, and this is what the distribution looked like. What we did is this. Like, okay, I got a low condition, I got a high condition, problem solved. However, there are different numbers of items in these conditions. So this condition with 20 items is going to have a more reliable mean, theoretically, than the ones with fewer, especially to the extent that the hardest ones are going to have missing trials that limits the number of responses available. It's also assuming that the difference between these two items, which one is low and one is high, is the same as the difference between these two items, in which one is low and one is high. And that should make you feel uncomfortable. Anytime that you take a continuous variable and you cut it up, you are introducing measurement error voluntarily. That is usually not a good strategy. And it wasn't a good strategy here. The next problem is about this, again, artificial dichotomy between what is a young adult and an old adult. In our case, we had no one in the middle, so we couldn't do much better than that. And most of the younger adults, by the way, were just a college age sample. But people aged 65 to 86 are not nearly as homogeneous of a group. There's way more variability in performance across 20 years of life, especially towards the end of life, than there would be within a 3-year range among people who are largely from the exact same circumstance. So this needed to be treated as a more continuous variable too, by also trying to respect the idea that we don't have any middle-aged adults to try and fill in the gap. So what we can do, though, is fit what is known as a piecewise slopes or a spline model to be able to deal with this. So if we have our 20-year-olds over here and we have our 65-year-olds over here, we have one mean difference that we can put in the model as to whether you're in the older group or the younger group. Within the older group specifically, if we put in a slope for how much older you are than 65, and we see that that slope has, say, a positive effect, I would call this an aging effect, because it's not just that you're in the older group, it's that you're older than the rest of the people in the older group and that matters. In contrast, if I've put in a slope for a number of years over 65 and it didn't matter, if it's mostly flat, then I would call this a cohort effect. Like, it's not aging that we're looking at, it's some other thing that's related to age, because if it were aging, you would see a difference between an 85-year-old and a 65-year-old. So this at least would allow us to look at within group differences within the older group specifically, because they're likely to be relevant. So, yeah. In addition to mean differences by age, there's variance differences by age. So we would not assume that the younger adults are as different from each other as the older adults are. That's an analysis of variance assumption. You should have homogeneous residual variances across your groups. The same thing would be true in this context as well, and I know it's not going to be the case. So we need a model that's able to allow different variability as a function of age and not just different means as a function of age. And so putting that all together, we need to have continuous predictors that differentiate our items and not artificially discrete conditions. We need to be able to allow missing response times under an assumption of at random, meaning conditionally random and not completely at random. We need to be able to model all the reasons why people differ from each other and why items differ from each other, not just the ones that we have in our data set. And we need to allow differential leftover variability for the younger adults than for the older adults. So this is the finale of chapter 12, gets us to the very last model. And in terms of the distribution of information going into it, in this case, it was 25% subject differences, 18% item differences, and the rest was residual. I was able to fit a model in which we had separate random intercept variances for older adults and younger adults, as well as separate residual variances for younger adults and older adults. And then we had an interesting pattern of a three-way interaction here, where in these plot we have relevance on the x-axis. So the negative slope means that response times decrease for changes that are more relevant, which is what we would expect. However, that appears to be the case in the younger adults, but only in the older adults with respect to trials that are of low salience. If it's high salience, then relevance doesn't matter as much. And so that created this three-way interaction term that the model is building up to. So I was able to build a model that had all the features in it through the magic of multi-level modeling. That's the take-home answer to that. Okay. Questions on that? Does that make you think of anything in your worlds that you want to do? Not yet? Here's another quick one. This was looking at eye movements. So this was eye movements during natural scene viewing, where we have multiple scenes, 67 of them, viewed a picture for 6 seconds. 53 subjects were randomly assigned to one of 4 viewing conditions. One group was told to just look at the picture. Another was told that they had to memorize the picture for an upcoming test. A third group was to rate the pleasantness, and the other one was searching for letters that never actually appeared. So when I got into this project, it was because I was a faculty member on the student's master's thesis committee, and this is what he presented to me. Well, we're going to do a mixed effects ANOVA. We're going to have my between group manipulation, and then viewing time, I'm just going to cut it up into 500 millisecond intervals. I was like, no, you're not. This is going to become a multi-level model. So it did. So in his data, he has individual eye movements during scene viewing as the level 1 response. So saccadic amplitude and fixation duration and stuff like that. And each of those eye movements is nested within subjects. Each of those eye movements is to a particular scene, and that creates this crossing. And I'll note we had almost 70,000 individual eye movements in this data set, so not collapsing over anything. Here's a picture of the predicted outcomes, but here's some more interesting pictures of where this came from. So this is an example scene. It shows a kitchen. This is the research team that was involved in the study. So Mike Dodd is the faculty member. He is laying on one of his graduate students because they thought this would be funny. So the background for this story, by the way, is that we had a department chair who was stepping down out of that position, and as like part of a thank you packet, we all took pictures of ourselves in our favorite chairs. And they wanted to break into my office. This was my office and my chair. And they're like, can we use your chair to take this picture? So they thought it would be funny if he put his legs on his grad student. And this was the student whose master's thesis it was. Hi, Mark, if you're listening. All of these people graduated and lived happily ever after too. But it ended up, what we did was functionally a growth curve model, because they were interested in how these eye movement patterns changed during viewing of the pictures differently based on what the condition was, what they were instructed to do. So the people who, for instance, were instructed to free view, like they had this pattern. We had people who were doing the search task had a pattern with no leveling off, so they were still trying to find the hidden letter, and their eye movements were continuously searching. But all the other groups showed these differences. And I don't remember why this matters, but you can read the paper and they can find out. So this is an example of a crossed model that also has a growth model component to it. And in terms of what went into it, this was a disappointing result. Do you see that tiny blue sliver right there? That's all the variance that had to do with which picture it is. So we do not have any predictors about which picture it is, and that's a good thing because it would have had basically no variance to explain. What they were interested in is which subject it is, and in particular, which condition the subjects were assigned to. And so subject variance, then, the best we could do would be 6%, if you think of it that way. But we ended up having random linear time slopes over subjects, which means that trajectory that we showed, each person needed their own slope of that trajectory, and that creates another variance component, another way that people differ from each other. And main effects of viewing task explained 32% of the subject intercept. Interactions of task by linear time explained another tiny percent of the slope variance, and then the quadratic part explains basically nothing. So this is like a hybrid of an experiment and a growth model at the same time. Last one, this is an example that is not a crossed model, but it's within the same vein. So this is a dual task study. That's Susan Kemper. That's her in the picture here. She was one of my advisors in grad school. She's retired, so she's living happily ever after now. She had a dual task situation where she was interested in costs for talking and movement. So she called it tracking talking, and the study is linked right here. So she had folks tell stories, answer questions about experiences in their life, and with or without, they were doing a mouse task where they had to follow the mouse around a cursor that was moving around a circle. And so she was interested in a lagged effect of interference. So to what extent does your current performance in tracking this mouse suffer if the next thing you say is more complicated, like you're planning your speech as you go, and so you can see that as worse performance during the planning stage, versus is it the production of the speech? So does current tracking suffer and become more variable immediately after you finish saying what you wanted to say and your brain sort of hiccups? I have that experience a lot when I'm teaching. So this is within subjects, lagged analysis of which of these things was tied together. And so there's the paper if you're interested in hearing more about that. But that's just another example of how these models can be used in experimental settings. So that's all I had about that. The reason that I wanted to show you these examples with at least a little bit of detail is because what I thought the next thing we could do would be is to show you how you would fit these models in R, for instance, using NLME or Elmer. Because that's really where the learning happens, is when you're just trying to fight through the connection of the ideas and the notation and the code and the outcomes. So let me just ask that. In terms of these examples, go back to the main list at the top here. So the 4 examples, which of these do you think you would be interested in seeing first? We can do Larry's subject by words, which is a simpler case. The visual search study, which is still just a crossed case with some additional complexities. Eye tracking, which is the most complicated one because it involves the growth curve component. And then speech within subjects, which is different. It would be more analogous to like a diary study kind of thing in terms of looking at lagged effects and stuff like that. What do you think? And if you don't have preferences, I will pick. Larry, okay, number 1. If I see Larry on Facebook, I'll have to tell him you all picked him. He'll be very happy. 2 or 3, 2 and 4. Okay, 1 and 2, it looks like are the most popular so far. 3 or 4, 1 and 2. Okay, do you think that would be useful? If that's what we did next week, is like walk through an example with the data. I can give you the data. So the way that I prepare examples is I will probably, since it's just an R, make a markdown type document, and then you can run things along with me. But if you don't want to run and you just want to take notes and listen, like I'll have it saved as a compiled thing that you can just look at as a HTML or a PDF. Does that work? That works. Okay. Any other software that folks use that you'd be interested in materials for? I might be able to help because I use a bunch of different packages. Nothing, just R? Is that because it's free or because that's what everyone you know uses, or both?
I have a question regarding software.
Yeah.
Do we focus mostly or only on frequentist approaches, or do we also touch on Bayesian modeling?
I would say that I have not had to teach Bayesian stuff very much, if at all, and so I would focus on that. But nothing should change other than the addition of the priors. Like all of the concepts and things like that would be the same. Likelihood ratio test would work a little bit differently, I think, but otherwise it should be similar enough. I can try to point towards other resources for what these models would look like in like BMRS or something like that, if that would be useful.
That would be great. Yes.
Okay,
Thanks.
I can try. That's what I can promise. M plus will, so everything M plus does with crossed models is in Bayes as well, and so I would feel less certain about that. Stan code, okay, that one I can't do. I can point you towards the workshop we did last year with multi-level measurement models, in which we had multi-level stuff and IRT stuff and then multi-level IRT stuff. That is on the same workshop page that I put in the chat at the front, but unfortunately I don't know Stan well enough to help you. Lo siento. All right, so then next week, I think we're meeting on Tuesday and Wednesday around the same time. Does that sound right? And I believe that was the end of part 1. So this is sort of we're making it up as we go along, kind of organizational structure, because when we were planning for this, we didn't know who would be in it and what they would need. So I think the idea, yeah, same Zoom link next week. I will send out an email with the Zoom link again, and with once I have new materials ready, and I'll also send out an email before then with where the video will be for this, so that way if you need to watch any of it again, you can, or you can just have it for posterity. The idea, I think, is for the folks who are coming back for the second half, which I think is most of you, then we could sort of talk about at the end of next week, like what that should look like, and then how we can extend these models. Like I know Thorsten had thought the transition into what this would look like for binary data, which heads us into the world of explanatory IRT, would be something that might be useful. but I'm open to other ideas as well. Okay, well then how about we call it a day? Sound good? All right. Let me know if you need anything. You have my email. Otherwise, have a good week and weekend, and I will see you on the next garbage day on Tuesday.
Thank you very much. Have a good day.
You too. Thanks for
Thank
being here.
you. Bye bye.
See you, garbage day.
Thank you.